All right. Conduction in steady state beyond 1D. What we have seen so far, up to the week before the break, was conduction in 1D systems, such as a wall or a thin boundary layer, right? Or in across, like jumping across the very thin gap that is generated by roughness between asperities. But not everything is a wall. Some things are cylinders, some things are spheres, some things are much, much more complex. This is what we're seeing this week. So let's. We already discussed the concept. Okay, let's see. Huh. Okay. Yes. Okay, we already discussed the concept of thermal resistance, and we spent half the class of today onto that. And if you remember, when we started earlier today, I said, from our differential control volumes unit, we could pick the differential equation we wanted for the wall, and then we solved it, and it was very easy. Let's talk about radial systems, and it's a unit in the book, and it's this unit here, where they get also happy with the differential equations. You have to know how you get there, and it's in the book. And if we have time towards the end of the week, I'll try to go over those myself. However, we know what the equation for heat conduction in a cylinder or a sphere would be, because we saw that in the differential control volumes unit. So we can take in those equations we can do exactly the same we did with the plane wall. Say is steady state, so the transient term goes away. We can say no heat generation, so the heat generation term goes away. And let's see. Okay, so the heat generation term goes away, and you end up with a ordinary differential equation of second order that tends to be very easy to solve, and you integrate twice. I'm not gonna do this integration now, but please look it up in the book, and we can discuss in office hours if you find it challenging. But essentially, you integrate it twice the same way we did with the plane wall, and it is all step by step in the book. So for the case of cylinders, we would get this heat flux, and from the heat flux, we divide by the delta T divided the heat flux will give us the resistance. And we end up following exactly the same steps as we did with the plane wall, with this resistance to conduction for a cylinder. Very important point here. In this case, the heat conduction is radial. So it's from inside a cylinder to outside, or outside to inside, but it's radially, it's not longitudinally. I'll touch on this again soon. So the formula for resistance in this case is not a 1D problem anymore, but we can recycle it because we have the same proportionality. And in this case is log of R2 over R1, and R2 is the outer radius and R1 is the inner radius, over 2 pi L. L is the length of the cylinder in this case, times 1 over K. We can calculate how much heat is lost by conduction in this cylinder using delta T over resistance. And the delta T, again, is temperature inside minus temperature outside. For example, if it is a cylinder carrying a hot fluid, and it's going to be high inside and colder outside. Much like we did with thermal resistance per unit area, we can define now for cylinders, like pipes, tubes, like all of you in ChE and petroleum engineering, this is what you want, right? Pipes. And in these pipes, what characterizes the pipe is the pipe can be more or less long, even if the diameter never changes. Having a longer or shorter pipe will have different effects for heat transfer. So we can have some sort of an intrinsic parameter by looking at the thermal resistance per unit length. Much as we did with thermal resistance per unit area, this is a horrible definition, terrible definition, but I cannot come up with anything better. So R prime means per unit length. However, this is not resistance divided length. This is resistance times length. And it's important to keep this in mind because we can get confused. The units would never match if we do it the other way around. And the formula depends only on the radii, the outer radius, inner radius, and the thermal conductivity. I have a formula. And the concept associated with thermal resistance per unit length is the heat rate per unit length. In this case, yes, heat rate per unit length is Q prime, which means Q divided by L as usual. For Q, it works. For resistance, it doesn't work. Right? For Q, it works. I put here a quick note that is the fact that we have a cylinder doesn't mean that the heat transfer is radial. Heat transfer is radial in a cylinder when the inner diameter and the outer diameter have different temperatures. But it can perfectly be that our cylinder is all isothermal in each cross section and along the length has a gradient. So one end has a temperature and the other end has other temperature. So this is very important. When I teach this live, I can see if people get me or not. A cylinder looks like a cylinder to all of us humans. And we might wonder what part of cylinder we don't understand. But let me tell you, no, we understand close to nothing about a cylinder until people tell us more. If they say the cylinder is hot inside and cold outside, I would use the formula for thermal resistance that is for radial systems. That is this formula with a log. If you show me exactly the same cylinder, but you tell me inside the cylinder and outside the cylinder is always at the same temperature, but left end and right end are at different temperatures. Oh, completely different problem, completely different problem. Actually, in this case, becomes a 1D problem in Cartesian coordinates. The formulas in this case, which I work here, are the same formulas we would use for a wall. Of course, it doesn't look like a wall, it looks like a cylinder, but the formulas are the same as those of the wall because it's a 1D heat transfer in Cartesian coordinates. So, very important to keep in mind. If you see a cylinder, don't jump to conclusions until somebody tells you what the boundary conditions are. Okay, good. And the good news is, whatever it is, there is a thermal resistance which we know how to calculate. Very powerful. Now, we just have to know what questions to ask to make sure we use the right formula. For spheres, we can do the same. We go to our differential control volumes unit. We see the equation of heat transfer in spherical symmetry. We take away the transient term. We take away the heat generation term. And we end up with a second order linear ordinary differential equation, which is very easy to solve by integrating twice, and it's done in the book in the sections that are marked here. And you end up using the definition of resistance, doing resistance is delta T over Q, you end up with this formula for resistance, which is tabulated in all the previous formula sheets that you're going to find from previous year's exams. And it's in the book too. And it's in these notes too. I'm going to show you in a second. So now we can have problems that are not 1D, that can be 3D, such as spheres, or can be cylinders, right? And we can do them. We can treat them that we couldn't before. Look, here is, you have the formulas for thermal resistance, for they call it cylindrical wall, right? Like, yeah, it's the wall of a cylinder, the wall of a sphere, right? How to calculate the heat rate, the heat flux, and the formulas for temperature distribution that I'm not too worried about those right now, but those come from solving this differential equation. You see here we have the differential equation that we're solving. They look complex. They are not complex at all. We solve them by integrating twice straight out. If you're curious, we can discuss in the office hours. I'd love to. It's all in the book stepwise. So let's talk about an example. Let's talk about the overall heat transfer coefficient in a pipe. We're talking about like what the soul of a heat exchanger. We're getting deep into what that is. So in this problem, we say, consider it's a long steel pipe that is 20 millimeters in outer diameter, and it's a 1 millimeter wall thickness, and it has pressurized water inside and is losing heat to a colder environment, for example, the shell side of the heat exchanger, by natural convection. The thermal property of steel, we have the thermal conductivity, 60 watts per meter Kelvin, ballpark, but easy to remember. The convection coefficient of the pressurized water inside, let's say, is 1,000 watts per meter square Kelvin, because let's say is in liquid state and with forced convection, and the inside and at the outside of the pipe, let's say, is just still air, right? Not a good heat exchanger in this case, but let's do this just because it's going to be good for us to understand, right? Is losing heat by natural convection with a convection coefficient of 10 watts per meter square Kelvin. Calculation, the question is, calculate the overall heat transfer coefficient. Before I do anything else, I would like to hear if your thoughts about, do you expect the convection against water, or the convection against air, to be dominant for this problem? Do you expect to have, do you expect water and air to have comparable effects from the point of view of thermal resistance? So we have water with a convection coefficient of 1,000 and air with a convection coefficient of 10 watts per meter square Kelvin. What is the implication of this from the point of view of thermal resistance? I'll tell you now, one of these two is dominant. Can you imagine, well, convection would be dominant, and the answer is true, but which one, convection, are we talking about? Are we talking about natural convection of air, or forced convection of water? Well, if water is dominant, I have a suggestion for water being dominant. That means the overall convection coefficient would be close to that of the water. However, if the water has a convection coefficient of 1,000, that means the resistance is fairly low, and the air has a convection coefficient of 10. That is a very bad convection coefficient. So that's a high resistance. And in this series circuit, as the heat goes through the water, through the pipe, through the air, yes, air, absolutely. Air is the dominant resistance. But let's see it. I just wanted, before we write numbers, before we write equations, it's good that we feel it in our heart. Eventually, we have to write it. But for equations are good for very little if we don't start with a good intuition. And that's what we're trying to develop as we learn in this class. So what is the overall heat transfer coefficient, which is tabulated for heat exchangers? So in this case, we're calculating it. So in this case is U, that's equation is 1 over R double prime total. That is 1 over R total times area of reference. We have to choose an area of reference. The pipe has an area inside and an area outside. Just for this problem, I'm going to pick the area outside. There is no universal convention about which area you should pick. You can pick inside or outside and you'll be a happy person. Maybe you'll be in a job in which they want to design heat exchangers or insulation of pipes with a diameter outside. Whatever you pick is not going to change your result. Doesn't change the total resistance. It's going to change what you call the overall convection coefficient, but you end up multiplying by the same area again. So we chose the outside of the pipe, in this case, as the reference area. Our equivalent circuit now, look at the beauty of this. Now we're using the concept of thermal resistance for something that is not only complex because we have forced convection of water, natural convection of air, we have convection through a non-Cartesian system. The complexity of this problem is enormous if you don't use the concept of thermal resistance. But we will use it, and it's not complex anymore. So this is a series circuit. Heat from the water has to go first through the convection of the between the water and the pipe. We will learn how to calculate that H like dead on, but for now I call it 1,000 just because it's handy to remember. And then it has to go through the pipe in which it has thermal diffusion that is in steady state and no heat generation, but it's not 1D, it's in 2D because it's opening up as it goes through the cylinder radially. And then has to go through yet another convection coefficient of air outside the pipe. This is the equivalent circuit. This battery here indicates the temperature of the fluid inside. This other battery here indicates the temperature of the air outside. This first resistor is convection inside. Okay, let's do the resistance. The resistor in the middle is the thermal resistance of conduction through the pipe. And inside the pipe, we have convection captured by this resistance. And outside the pipe, we have convection again against air in this other resistance here. We're pretty good. We're forgetting about radiation, for example, but we're good. What is this node here? This represents the surface temperature of the pipe inside. And this other node represents the surface temperature of the pipe outside, which we do not know. All we know is the temperature of the water inside, and we know the temperature of the air outside. So resistance of convection inside would be 1 over area inside times HI, right? And we can calculate. Here is the type of thing that when you're a student, you can do, but if you don't learn now, it's going to be so difficult later in life. check out the subtlety of the subscripts here. Here we have 1 over h inside, and here we have 1 over h outside. That part is kind of easy, but look, for convection inside, we have to use the area inside. And for convection outside, we have to use the area outside. If the wall is thin, we don't really care. But if the wall is not thin, for example, fiberglass insulation of steam pipes, you better know which is which. And it's all in these tiny subscripts here that are so easy to overlook. The first time I taught this class, I made a mistake with the subscripts myself. It's terrible, but I don't, seldom, because now I'm paranoid. So I calculated the resistance of convection inside and outside, and the resistance of conduction through the pipe. We use the formula that is tabulated and comes from integrating the differential control volume of week 4. And we have the formula here. When we put the values of the diameter inside and outside, right? The ratio of radii is the same ratio of diameters, and we get these resistances. And here we have the values. Resistance in convection inside water against pipe, resistance of pipe, and resistance of convection of air outside the pipe. Total value is the sum of all these three. From the point of view of plug and chug, this was trivial. This is like very mechanical, just get the value, put it in there, and however, what we wrote here has lots more information than a dumb result. Look at this here. We have the sum of inside pipe and outside. Does anything stand out to you? Look at this. This is 0.01 something. This is 0.000. I stopped caring. This is 1.6. This is the resistance of natural convection outside the pipe. This is dominant. Look, the total result, 1.6, is not all that different than this 1.59. So if somebody told you, okay, I don't care about the resistance of the pipe itself, you'd say, okay. Somebody would say, I don't know what the convection coefficient inside is. You can say, okay. Somebody told you, you know what, I'm going to neglect convection outside the pipe. You go, oh, no. You cannot do that because that's the dominant one. If somebody asked you, if you show these results to your boss and says, okay, I want a better number, if you're going to make an effort to get a better prediction, you might want to go and sharpen your pencil on how to calculate convection outside the pipe as well as you can, because these other two are very small. 10% error here is 10% error overall, but 10% error in either of these two translates to a very small percentage of error. So good engineers are the ones who know where to put the effort and where to cut corners. We must cut corners. We cannot get anything done if we don't cut corners. But when we cut a corner, we don't want to be something that ends up like causing us trouble. And we get to see it here in these resistances. So now that I have the total resistance and I have defined a reference area, I can calculate the overall heat transfer coefficient U. Look at this very important thing. We said that the dominant resistance was given by the convection to the air outside. when I look at the overall heat transfer coefficient, is dominated by the convection coefficient outside. And see the value we get, 9.886. What convection coefficient had we used for outside? 10. This is almost exact. So if I somehow, because I'm a very old and experienced engineer, I can anticipate that the convection inside didn't matter, and I could anticipate that the thermal resistance of the pipe didn't matter, which, parenthesis, by the way, that's the way you design heat exchangers. The last thing you want is to design that the pipe is part of your thermal resistance, because that slows down your heat transfer. So based on that knowledge, I could have said, you know what, the overall heat transfer coefficient is more or less 10, right there. Of course, we wanted to go step by step, and in the exam, you will go step by step. But here you get to see how mature engineers, these senior engineers, like very quickly, no, this matters, this doesn't matter. And overall, and in the end, they end up getting something that makes sense. Okay, so it's 1:50, it's time to stop. I'm going to rejoin at 2 again for office hours. Thank you very much to everybody, and I'll see you later today or on Wednesday. Till then.